Hello and welcome back to the video lecture series for ECE-340. I'm your instructor, Dr. Bradley Duncan. Today we're going to be looking at curve fitting and linear regression. Actually, we're going to look at linear regression first, and later on we'll look at higher order polynomial curve fitting techniques using some simple MATLAB code. In all cases, the material I'm going to discuss today is aimed at working with experimental data that may have some randomness associated with it, to allow you to get a better understanding of the way an experiment might be behaving, for example. So let's begin by looking at linear regression. Linear regression. So we're going to assume that you've gone into the lab, you've collected some data, and you've got a collection of data points in some set R, Xi, Yi. This is a collection of data points that to your eye, maybe you've plotted these points out on a piece of paper just to kind of get a handle on what they look like. And to your eye, it looks like this set of data is roughly linearly related. So it's a collection of data points that appear to be linearly related. Okay? Now recall that the equation of a straight line is y equals alpha x plus beta. Beta is my intercept term, and alpha, of course, is my slope. All right. What we are going to try to do is we want to choose alpha and beta so that when we set up our equation, the function y evaluated at my data points x sub I, which will equal alpha x sub I plus beta, we want that to be approximately equal to, as close as we can, the y sub I data point. All right? We're going to choose alpha and beta so that my straight line curve evaluated at my x sub I data points is approximately equal to my y sub I data points. All right, we're going to seek we'll seek an optimum alpha and beta by minimizing a collective error term that we're going to call little epsilon. All right? So let's write down what my collective error term looks like. I'm going to define it this way. Epsilon equals summation I equals 1 to n. Little n is the number of data points in my data set. Y sub I, that's my data point, minus y evaluated at x sub I, that's my estimate, squared. N equals number of data points. All right. This y is my prediction. This is my yi data point. This is what I call my collective error. And the reason I call it collective error is because I'm adding up all of the errors for all of the possible data points. All right? Now, in just a couple of seconds, what I'm going to do is minimize epsilon by taking derivatives of epsilon with respect to alpha and beta and setting them equal to 0. It's relatively easy to take the derivative of a function that's squared. You'll notice my collective error term here includes that power of 2. The reason I'm doing that is I'm making the errors all positive. You might at first say, let's throw in some absolute values, look at the absolute error between my data point and my predicted value. That's hard to take a derivative of. If I square everything, however, it makes all of the errors positive. All right? So that power of 2 there makes my error values positive. Makes the errors at each data point positive, and it allows me to take a derivative easily. Okay? All right. All right. So, let's remind ourselves at the top of the page here what our squared, what our squared error term looks like. Epsilon equals summation I equals 1 to n yi minus y evaluated xi quantity squared. All right. Now we're going to seek an optimum alpha and beta, and the way we're going to do that is I'm going to write down two equations. I'm going to take the derivative of epsilon with respect to alpha, and I'm going to set that equal to 0. And the derivative is, do a couple steps here. Alpha naught and beta naught are my optimum alpha and beta terms. I go ahead and take this derivative. I get a negative 2 times summation I equals 1 to n of yi minus alpha naught xi minus beta naught times x sub I. All that's inside of my summation. I'm going to set that equal to 0. We'll simplify this in just a second. Similarly, I'm going to take this is my second equation. I'm going to take a derivative of epsilon with respect to beta, and I'm going to set that equal to 0. And just like above, I get a minus 2 summation I equals 1 to n of y sub I minus alpha x sub I minus beta naught. Okay? So remember how you minimize a function. You minimize a function by taking the derivative and setting that derivative equal to 0. In both cases here, alpha naught and beta naught are optimum. Alpha and beta values. They're going to be the ones that minimize this squared error term, which is a collective error term when considering all the data points in my data set. Okay? All right, so let's rewrite equations 1 and 2 here a little bit. Let's simplify them just a little bit. So equation 1 becomes alpha naught times summation over I x sub I squared plus beta naught times summation over I of x sub I, and that will equal the summation over I of xi, yi. Okay? All right. Next thing is equation 2. And this can be rewritten as alpha naught times the summation over I of x sub I plus n beta naught, and that will equal the summation over I of y sub I. All right, so we can very easily, by looking at the second equation, I'm going to divide by n everywhere and solve for beta naught. And then I'm going to plug beta naught back up into equation 1. All right, those are the steps I'm going to do. I'm going to take that second equation, I'm going to divide by n and solve for beta naught. Then I'm going to plug beta naught back up into equation 1 and solve for alpha naught. All right, let's do that. What we find is that beta naught equals y bar minus alpha naught x bar, where y bar equals 1 over n times the summation I equals 1 to n yi, and x bar equals 1 over n summation I equals 1 to n x sub I. These two are called sample means. All right, just take my y data values, add them up, divide by the number of points. That's the sample, that's the mean of the samples I have for y. Likewise for x, I add up all my x values, divide by the number of data points, and I get a mean of the sample values in x. Okay? I'm going to plug beta naught now back up into equation 1 from the previous page. And so equation 1 now becomes this. And I'm going to divide by n. You'll see this in just a second. Get an alpha naught, divide by an n, summation over I of x sub I squared plus y bar minus alpha x bar over n summation over I of x sub I, and that equals 1 over n summation over I xi yi. All right. Continuing on, we get alpha naught over n summation over I xi squared plus y bar x bar. You'll notice that my summation over x right here divided by n is my sample mean in x. Continuing on, I get minus alpha naught x bar squared, and that will equal 1 over n summation over I xi yi. And pull some terms together. I get alpha naught times 1 over n summation over I xi squared minus x bar squared, and that's equal to 1 over n summation over I xi yi minus y bar x bar. solve for alpha naught, and then I get this. That's that. Okay. Let's go to the next page and write a summary down. Summary. This is what I'm looking for. I'm looking for y evaluated at x sub I, it's one of my data points, equals alpha naught xi plus beta naught, where xi, yi is data, and alpha naught and beta naught minimize my collective squared error term epsilon. Alpha naught and beta naught are y bar minus alpha naught x bar. Calculate that one, and then alpha naught is n x bar y bar minus summation I equals 1 to n xi yi divided by n times x bar squared minus the summation I equals 1 to n of x sub I squared. And in all cases, x bar equals 1 over n times the summation of xi data points, and y bar equals 1 over n times the summation of y data points. So those two are my relationships for optimum, alpha, and beta. All right, so let's do some examples and play with some real data. Here's a data set that I pulled out of a textbook. I use the relationships on the previous page. Use those relationships for alpha naught and beta naught. And this is what I came up with. I did this by hand using my calculator. I'd like for you to check me on this. What I found was x bar was 2.605. Okay? And I found that y bar is 12.436. Clearly I have n equals 10 data points. I also found that the summation of the x squared values was 85.3277, and the summation of xi and yi products was 358.7337. Did that using my calculator sitting at my desk. Plug that into my alpha naught and beta naught equations from the previous page, and what I found was alpha naught was about equal to 2, and beta naught was about equal to 7.25, which means that my best fit linear curve is y equals 2x plus 7.25. That's my best fit line. Okay? All right, so Then it occurred to me, heck, let's use MATLAB. So I went and wrote myself a MATLAB program. And I've made it available to you. The MATLAB program I wrote is called Linear Regression Example.m. Please download that, take a careful look at it, and study the steps and make sure you understand what's going on. MATLAB gave me, I just programmed in the equation for alpha naught and beta naught, and MATLAB spit back to me, said my alpha naught was approximately 1.9909, and that's about 2, like I found using my calculator, and beta naught was 7.2497, and that's about 7.25, like I had calculated earlier. And what I then did was I calculated the best fit line over an extended range of values, and this blue line here is my best fit line. All right, I plotted it over an extended range of values. I also calculated the correlation coefficient. Calculation of the correlation, we discussed correlation coefficient in a previous video lecture. And in one of your assigned reading sections for this module, you'll see how to calculate the correlation coefficient using data. It's really quite simple. What we found when I used MATLAB to calculate the correlation coefficient was a little bit bigger than 0.7. Now what does that mean? That means, remember, correlation coefficient tells me as the one random variable, for example x, goes up, about 70% of the time y is also going to go up. All right, and the data looks to me to be generally linear related. The correlation coefficient backs that up. And I'll just point out that if the correlation coefficient was unity, then all of the red circles would fall exactly along the blue line. All right? That's what that would mean. All of those data points, all the y data points, would squash down and fall right along the blue line. All right, so make sure you do download the linear regression example. We'll show you some interesting steps in there. All right. What about polynomial curve fitting? What about polynomial curve fitting? What if your data looks like it maybe falls along a quadratic type function, a squared function? What if it looks like it follows a cubic type function or some higher order function? We can fit that too. I'm not going to calculate this out by hand. We'll use MATLAB to do this. So we'll assume our data we'll assume that our data, according to our eye, we plot the data points out, sketch it out, and it looks to us like it follows, the data behaves according to some higher order polynomial fit. All right. So a lot of textbooks will write a polynomial something like this: y equals a plus bx, that's the linear part, plus cx squared plus all the way up to dx to the nth power. Okay, so this would be an nth order polynomial. All right, nth order polynomial. It requires m plus 1 coefficients because of my last value here, a. So I require requires m plus 1 coefficients. Alright? Now that's the way an mth order polynomial is commonly written in a lot of textbooks. However, we're going to use MATLAB, and MATLAB assumes the polynomial is written in a slightly different way. MATLAB. MATLAB notation. In MATLAB, the coefficients are ordered like this. Y equals P1 x to the mth power plus P2 x raised to the m minus 1 power plus dot 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 plus P sub m times x plus my constant value P sub m plus 1. All right. In MATLAB, we can find P, which equals P1, P2, P3, PM, Pm plus 1. This is a one-dimensional vector. We can find that one-dimensional vector using the polyfit function. P equals polyfit x, y, m. All right? So my 1D vector up here, you'll notice this 1D vector has m plus 1 values. M plus 1 values. M there is my order of my polynomial. To fit an mth order polynomial, I need m plus 1 coefficients. X and y here are both 1D data vectors. And P here is that P. All right, P is a m plus 1 linear 1D vector. All right, so that's the notation that we get from MATLAB. All right, our best fit curve is then found using the polyval equation or function in MATLAB. So let me remind you here. Polyfit P equals polyfit x, y, m. This yields an m plus 1 element vector. Best fit a vector of coefficients. The polyfit function in MATLAB gives back to me a vector P that has m plus 1 elements, and those elements are the coefficients for the best fit mth order polynomial curve. Okay? Now, we can then use the polyval function, let's say to plot, for example, my best fit curve. to plot out my best fit curve, I'm going to use the polyval function. And y equals polyval p comma, those over tildes, I'm just trying to distinguish some x's and y's here. I'm not trying to be mysterious. X tilde is an extended range of x values. It doesn't necessarily, x tilde doesn't have to necessarily be just the x data points. It could be an extended range of values over which you'd like to plot your best fit curve. Extended range of x values over which you want to plot the best fit curve. Okay? Extended range of values over which you would like to plot the best fit curve. And the y tilde values are the corresponding y values that you would plot. All right? That's all it means. A couple other things I should point out is when using polyfit, if m equals 1, p is a 2-element vector, and it yields the linear regression coefficients. This is linear. So if you want to do linear regression using MATLAB, you can program in the alpha naught or beta naught equations that I derived for you earlier, or you can just use the polyfit function when m equals 1. It'll be happy to do a linear regression curve fit for you as well. Okay, and I should also say this, the polyfit function does indeed minimize a squared error term, but it gets really complicated. You can end up with multiple equations, multiple derivatives of a complex squared error term, and you have to take derivatives of that squared error term with respect to all of the coefficients and solve matrix equations, and it gets kind of nasty. MATLAB's happy to do that for you, though. All right. Let me point out a couple of cautions when using higher order polynomial fitting. Caution. Fitting your data to a arbitrarily higher order polynomial is not necessarily always the best thing to do. Higher order polynomial fits are not necessarily always better. Okay? So, in particular, we'll see this now, if we have n data points, and m equals n minus 1 polynomial, we'll go through all of the data points if we have an n data points and m equals n minus 1 polynomial, we'll fit all of the data points with exactly 0 error. I'm going to show you an example in just a second. As a preliminary example, let's talk about this. Our earlier data set, way back up there, has 10 values. So let's assume we have n equal 10 data points. N equals 10 data points. And m equal 9, ninth order polynomial. And a ninth order polynomial will require m plus 1 equals 10 coefficients. All right? This requires, this will ultimately, we're not going to do this, but this would require 10 derivatives of some squared error term epsilon that we would then set equal to 0. And I haven't shown you what epsilon might look like for a 10th order polynomial fit, but epsilon in this case is a collective squared error term for some higher order polynomial. So this would require 10 derivatives of epsilon that would all be set equal to 0. All right? And then we would solve 10 equations in 10 unknowns. Let's solve 10 equations and 10 unknowns. And because I have exactly 10 data points, I will end up with exactly 0 error. My ninth order polynomial will go through all 10 data points with 0 error. Solve 10 equations and 10 unknowns. The fitted curve will then go through all 10 data points with no error. Meaning that epsilon in this case, if I have 10 equations and 10 unknowns and 10 data points, epsilon can be set exactly equal to 0. All right. So back to my linear regression example equation or MATLAB program. Once again, please download that. Take a look at all the steps. This is the same data set that we've been talking about all along. I have 10 data points. 10 data points. I used MATLAB and calculated a ninth order regression fit that we see here in the blue curve. You can see that the blue curve goes exactly through all of my red circled data points. Okay? And it does so with exactly 0 error. However, I claim to you that that ninth order regression fit is more or less useless to me. We saw earlier that X and Y have a correlation coefficient of about a little over 70%, and that the best fit curve was actually something like that. All right? The blue ninth order polynomial fit is almost certainly not helpful in this case. It provides no measure of data smoothing for us. and it doesn't allow us to make reliable predictions for y given some value for x. So, for example, I might be interested in extending this curve out past my data. My green curve could allow me to get at least a reasonable estimate. If x is, for example, 6, a reasonable estimate for y will be up in this range, be about 22, 23, something like that. Okay? According to the green linear regression curve. My blue polynomial fit, however, seems to indicate that my y values shoot down towards negative infinity as x increases. That's just not likely the case. So higher order polynomial fitting is not necessarily always better. What you want to do is try to choose a polynomial order that actually fits your data pretty well. Okay. That's all for today. As usual, if you have any questions about the material I've discussed, please contact me at your earliest convenience, and I will answer all questions as fully as I am able. Have a nice day. Bye-bye.